Okay, we're ready.
Okay, I think it might be okay. Oh no. I don't hear anything anymore. Okay, maybe it is. Brad?
Yeah, we can hear you.
Okay, good. All right. Okay. All right, we'll find work on your. Okay, should we start, or are we still waiting for people to get here?
Go ahead.
Okay, so basically, I want to try to give people kind of a simple plan for evaluating and improving the solver performance for these kind of tectonic problems. And in order to do that, you need some general background, but you do not, in any sense of the word, need to be an expert on the solvers. And I guess I just want to give an analogy because I think it's helpful in the way that these things should be understood. It's very, very similar to when you work in a lab and you have a piece of equipment, say like a lock-in amplifier. In order to use it, you have to know a lot of the specifics about the design. What is the input impedance? How are the scales on the dials, and what can you do? But you really don't need to understand how it's constructed internally in order to make good use of it. And so I think the same thing about solvers. You have to know basic things about the operation. You have to know what your alternatives are, and you have to know how to get more information about what happened in the solve. But you don't have to understand how they're constructed in the back end or why they work mathematically to use them efficiently. So what I want to do here is show you how to look at your solver performance and then show you how to optimize it for particular problems. And by optimize, I mean sometimes it won't converge and you make it converge, or sometimes it converges slowly and you make it converge faster. We're not going to talk at all about performance optimization for scalability or serial performance optimization. Those are separate topics that are more involved. So let's begin by talking about how you control the solver. Just like PyLith, all of PETSC can be controlled by options in the options file. So for a raw PETSC program, the options look like this, like the KSP is a Krylov solver. It's a linear solver. So FGMRES is a well-known type of linear solver. And these things can have prefixes just like in a PyLith option file. If you're using PyLith, which you are, then any PETSC option can be given with the prefix --PETSC. The most frequent option that I use is --PETSC.startInDebugger, which will spawn an instance of the debugger and attach it to your PyLith run. And I use this all the time for debugging things. I think it's a key thing to know. Now, what I'm going to use to look at controlling the solver for raw PETSC things, I'm going to use example 19, and I think that mostly I'm just going to use that for demonstrations of nonlinear problems because that's a lot less developed in PyLith. We know how to solve nonlinear systems, but we haven't spent a lot of time looking at how you optimize for that, how you deal with different kinds of nonlinearities. We will, but we've been much more focused on the linear part. So I will show you things about linear solvers with the PyLith example, hex 8. Although I could have used TET4 or the 2D examples, these solver options will work equally well. And so I'll go over that again when we get there. So let's start with the basics. I think these are the very, very basic things that you ought to know about the kinds of solvers that we're using. Pilot is going to use a Krylov solver. And the reason we're going to use a Krylov solver is that these things operate just by using the action of an operator or a matrix. A matrix is a finite dimension, a discretized operator, linear operator. And so just by using the action, as you can see, A times an initial vector, A times that again, and so on, we can build an approximation to the solution of an equation. And what happens is you take a very, very large system, you act with the stiffness matrix a bunch of times, and this generates a small system which can be solved exactly, and that generates a guess for the big system. This is a pretty effective way to solve huge systems of equations, systems which you cannot directly factor if you're familiar with the factorization techniques that you learned in linear algebra for very small systems, 5 variables or 6 variables. Those don't scale up very well to large systems, and you're forced to do something like this. About Krylov solvers, they do not solve equations per se by themselves usually. They just get better approximations. So they need what's called preconditioners, which is a co-solver. The Krylov solvers help you improve a guess, so they're iterative rather than being like Gaussian elimination. But they need help. And so what we do is we combine the Krylov solver with something else to get an efficient solver. And the other thing to recognize is that they are effective in basically solving the coarse parts of the problem. They can do well on averages. What's the average stress? What's the the main variations away from the average and things like that. A preconditioner is kind of a co-solver that you use with the Krylov method, and we're going to refer to it as M. So what you do is on each step of the Krylov method, you do a subsolve. You solve with M. And you can phrase it in the linear algebraic way with this equation right here. M inverse AX equals M inverse B. So you can sort of view it as solving a different equation. M inverse A is a new operator. M inverse B is a new set of forcing functions, and I solve for X. And hopefully the new operator, the effective operator, is easier to solve. Now, in order for this to make any sense, preconditioners should be inexpensive because we have to keep using them all the time. And, of course, they should accelerate the convergence or you wouldn't do anything. So let's step back and go through a series of steps that one might when you want to solve, let's say, a system that gets generated from pilot. So you have a PDE, you discretize the PDE, so you get a set of algebraic equations, and then you'd like to solve this. Well, generally what you do is you always start with Gaussian elimination, or what's called LU factorization. It's not iterative, so you get the exact answer. There's very little hidden dependence on stuff like how big or small your numbers are. And it's a very good check that you've produced a consistent system, that it's not singular, that you haven't made a mistake somewhere. However, there are, this is perfect, but you can't do this for all problems. For instance, in parallel, you need to go get a third-party package, which you can do when you build your PETSC, like mumps or SuperLU. Mumps is from INRIA, and SuperLU is from Berkeley. So you can do this. However, It doesn't always work, especially with the kind of problems that Pilot generates. It doesn't work for singular problems. Now, we don't generate singular problems because they're not physically meaningful. But we do have saddle point problems, and LU cannot normally handle a saddle point problem because it has once to divide by the diagonal element, which is 0. We can get around this, however, by employing a slightly more involved solver, which we'll call, which PETSC calls a field split preconditioner. What is that? It's just a way to divide sets of equations into more than one part and solve the parts separately and then combine them. So, for instance, if you have just a purely elastic problem, you can use factorization, get the exact answer, and it's very nice. But if you have elasticity and a fault, then you generate a saddle problem because the fault does not have any self-energy. There's a 0 block on the diagonal. And so what you want to do is, if you want to do this exact method, you solve separately the elastic part and the part associated with the fault tractions, and then combine them. And this is what's called a sure complement here at the bottom. Sure complement is the way of factorizing into 2 pieces any given operator. PETSC can do this automatically, but you probably won't use this because we do it automatically for you in Pilot as well. So let's look at what happens when you solve stuff. And you may have already seen this in some of the tests with Brad and Charles, but I want to go over it again. So in order to understand what solver you actually ended up using, we have these view options that you can give. And you'll see this in normally in the pilot.cfg or pilot.app.cfg or the particular CF config file you're using. This SNES is the simplified nonlinear equation solver, and the KSP is the linear equation solver. And what it does is it prints a little report that tells you what the solver was doing. Oops, sorry. And since we dynamically assembled the solvers, you can't look in the code and say, oh, there's what the solver was. So this is invaluable in telling us what happened. I wonder if there's a little, I'll get the little arrow. Okay, so, oops, it's moving my slide. It's supposed to, Brad, is it supposed to move the slide? That's kind of not great.
Click, don't drag the arrow, but just click the area where you want it to appear.
Ah, okay, I see. It's hard for me, oh, now I lost my, okay. So the first thing that it tells us is that we have a linear solver, and it tells us, right, can't see my hand. There we go. So it tells us we have a linear solver here. Oh, I can't see where it makes my mouse go away, so I can't. The second thing it tells us, every object in the solver hierarchy has a name we call a prefix, and here between the parentheses is the name. So this is field split 0, which means it's the first field in the splitting, and that would be the elastic field. And we're going to use a solver of type GMRES or flexible GMRES here, and it gives us the number of iterations and the tolerances we're using, what kind of preconditioning, and whether it has a null space that we've let the solver know about. And so there's a bunch of information here, and this is where you want to go to see, okay, what have I done? And but that just tells you what you assembled. It doesn't tell you what happened during the solve. So in order to see what happened during the solve, you give a monitor option. So monitor the nonlinear solver, monitor the linear solver. And at the end of a run, you can get all the performance information with log summary. So for instance, if you monitor the nonlinear solve, what you'll see is these norms, and the norm is just the size of the residual for this set of nonlinear equations. So if your set of equations is f of x equals 0, which is how you normally phrase the nonlinear thing, then f of x is the residual, and you want to drive that to 0. So here we see the size, and so the norm will be sort of add up all of the components of that, or add up the squares of the components and take the square root, which is what we're showing here, the 2 norm. And you can see that it's converging fairly fast. That's a characteristic of Newton's method. If it converges fairly fast. Now we might say, well, at each of these Newton steps, we have to solve. So when we solve a nonlinear problem, what we normally do is it's an iterative process, and at each iterate you solve a linear problem. So we turn on also the KSP monitoring. So then there'd be a linear norm and another linear norm here. But typically, what we have is we'll have one linear solve, but for the outside, but inside we'll be solving other different linear solves. So for instance, here what we have is we'll have multigrid, and we will normally solve the elastic problem with multigrid. It's an optimal method for that. And so on each of the coarse grids, we have another linear solve, which you see here. We have on level 1 and 2, which indicates coarser things. Okay. So at the end of a run, if you give minus log summary, then we generate a table like this, and here's an excerpt of the table that gives you an idea of the performance of each part. And I think you should always start at the top level and look at performance, and then go down and see what occurred inside of that. So for instance, I show the nonlinear solve here, and then the linear solve and setup. So for instance, what's going on? So for Pilot, we generally have a nonlinear solve embedded in a time loop. So at each time step, we're going to solve a nonlinear problem. So the count is 1 because we solve one nonlinear problem. Each nonlinear problem is a sequence of linear solves. Here we have 3, so we converged in 3 linear solves for the nonlinear problem. And then here, KSP setup is the setup work that happens before each solve. Now, why are there 12 of them instead of 3? It's because each parallel component has to be set up too. So this was probably run on multiple processes. Lower level operations give you much more information about what the machine performance looks like. So for instance, here we can see that the vector dot products are getting 13 megaflops. I should put this here. Whereas the where's that? Oh. No, go over here. Over here. There we go. Whereas the matrix multiplication algorithm is getting 126 megaflops. So so here's where you want to go and look at serial performance. If you. Oh, really? Can you hear me now?
Can you start? Yeah, we can hear you now. Can you go back about 30 seconds to where you started talking about? Sure.
Okay, so these lower level operations are what you want to use to assess the how well you're doing on a single processor performance, and a little bit about how you're doing in scalability. So looking just at a full solve, it's very hard to interpret most times what's going on. So you look at the numbers for a SNES solve, it's hard. But if you go down and you say, well, let's look at dot products. So this VEC multiple dot product is running fairly slow, 13 megaflops. So what does that say to you? Normally, you'd like to compare it to, a VEC AXPY or just a VEC scale, because what that would show you is don't need processors to talk to each other, whereas a dot product does. Everyone must agree on the value of the dot product. And the fact that it's so small indicates that the network on this machine is very slow. So, for instance, looking at matrix multiplication, the matrix multiplication is getting a much higher flop rate, and that's because it doesn't do synchronous communication like the dot product. So if you look at the paper that in JGR on Pilot, we give an analysis of the performance, and we show how to use these low-level operations to think about machine performance, and then the upper level, you try to optimize your upper-level operations to get the right mix of low-level operations to run faster. And you can get this information in a more usable format as a Python module if you'd like to automatically process it, for instance, or plot or stuff like that. You can get with -log summary Python, and that's how we did it for the Pilot paper. So the rule, I think, this is the rule for solvers, but I think it's really the rule for everything if you know what you're doing, is you start from a simple, slow, correct version, and then add stuff in tiny increments. So if you're doing a mathematical model with Pilot, you normally start from a very well understood scenario which you can solve and understand the result, and then you slowly add different features till you get to a research product. And it's very similar with solvers in that you start with the slow, non-scalable, guaranteed solve to check your physics and check your setup, and then slowly back off of that to get better performance and better scalability. So, by the way, by scalability, what I mean is that as you add more processes or more parallelism, your time goes down accordingly. So a scalable solver, if I add twice as many processes, should take half the time. If I add twice as many processes and it takes about the same time, then it's not scalable. So the first thing you can do is to weaken the linear solver. We always start with FGMRES because it is a monotonic solver. It never goes into oscillation. If you run it longer, your answer will get better. But it uses a lot of memory and it uses a lot of synchronization. So on bigger clusters like we're running for the Pilot paper, we want to kind of minimize the amount of dot products we do. And so there's things like, this is called bi-CG stab, bi-conjugate gradient stabilized, are more efficient for larger machines. And so you can try, they might run a little longer, they might take more iterates, but overall it would be less storage and faster time in some cases. And there's a bunch of variants of this. So everything in this talk that's magenta here, like the word table, is a link. So if you click this link, you will get a table of all the solvers and preconditioners in PETSC, and there are a lot. And I don't think it's really useful to go over a taxonomy of all these things. What I do think is useful is looking at some papers where people have solved problems similar to yours before. Because the real strength of PETSC is that you can get a paper that's with a problem that's similar to yours and construct the solver that was used in that paper in a matter of minutes. And you construct it all from options, command line options. And we've done this several times. There are maybe 20, 30 papers on this full Stokes ice sheet modeling, and we can run all of those just from command line options, and therefore we can test them all against each other. And that's really the point of PETSC, is to be able to do these things. And so for Pilot, you can take a solver that anyone's used, although I'm not sure who is doing really advanced solvers except us. But should someone do it, you can reproduce it. And should anyone have an idea and tell you about it, it should be straightforward to implement that idea easily. And so that's what we want to provide, tools for constructing optimal solvers. So you can try weakening the linear solver. You can also try weakening the preconditioner, and this is going to be much more effective than the linear solver, but also a lot more difficult. You can try taking the LU factorization to an incomplete factorization. It does have less storage and work, but you lose all your guarantees of correctness, and it's just unreliable. And the best part of LU is reliability. So ILU, is just the only black box thing you have to try. Other things really depend heavily on the analytic character of the problem, on the actual equations being solved. So what I usually say is there are no black box linear solvers. There are only solvers that are tailored to equations. There are parallel versions of ILU, but they are no more reliable than the serial version, and they're slower. So you can always try it. We'll talk about multigrid in a minute. I think one of our best options is what's called algebraic multigrid. Now, let me just briefly explain what the idea behind multigrid is, because I think the idea is generally enough to understand this slide. Multigrid is the idea that I can solve a simpler representation of a problem on a coarser grid, and by that I mean I discretize with a larger length. So instead of knowing stuff every kilometer, I might have data every 10 kilometers. Now, the solution to that problem will not have the fine details, but it might be close enough that I can use that solution as an initial guess for a solution for the 1 kilometer problem. And there are some more specific mathematical reasons that this works, in, normally phrased in terms of what mode in the air are you attacking. You want your solver to attack the high frequency modes first, because then on the coarse grid, those high frequency error modes are gone because it can't resolve them anyway, and we just treat low frequency modes. And so this is kind of the essence of why multigrid works. And so you need a solver that gets rid of the high frequency error modes, and then you can use it on a hierarchy of grids, and you can get a very, very efficient solver because coarse grid solutions are much less expensive. Because you need this, the solvers that people use on the coarse grids are often called smoothers because they get rid of the high frequency error components, meaning they smooth the air. Now, multigrid was invented for structured grids because it's very, very easy. You make a coarser structured grid, you can project everything from the fine grid to the coarse grid or back, and it's not hard to set up. It still may be hard to understand what solvers to use for the equation, but the mechanics of the grid management is not hard. However, the mechanics of grid management for unstructured grids can be very, very difficult. And in fact, there is no general geometric multigrid for unstructured grids because constructing coarse grids is very difficult. So the alternative is to take the matrix that is produced by a program like Pilot from an unstructured grid and just make simpler, smaller versions of the matrix that in some sense approximate the problem. And this is what algebraic multigrid solvers do. The nice thing is that algebraic multigrid doesn't need to know anything about your unstructured grid. It just takes the matrix in. And therefore, it can be easily interfaced to codes like Pilot through the generic matrix interface. These kind of algebraic multigrid has only been highly developed for elliptic problems, like the Laplace equation, elasticity, the Stokes equation. There have been several attempts to do this for hyperbolic problems, such as the wave propagation problem in the dynamic version of Pilot. But this is still a research topic and does not work in any freely available code that exists. So right now, we're just going to use algebraic multigrid to solve the elastic operator, which is elliptic. Now, that could be embedded in part of a hyperbolic type solve. So if we were going to invert that operator for some reason in a dynamic simulation, we could do it, but we wouldn't have the hyperbolic part in there. Now, you can try out algebraic multigrid from PETSC just by saying change the preconditioner type to something like GAMG is the built-in algebraic multigrid in PETSC. ML is a third-party algebraic multigrid package you can download when you configure your PETSC. It's from Sandia. Hyper is another one that you can download, and that's from Lawrence Livermore. The thing to understand about algebraic multigrid is what controls the convergence. There's two things. The first is the effectiveness of the solvers on coarse levels, but of course that's the same for any multigrid, and that we can do a pretty good job of. We understand how to do that in Pilot, and what's there should be good. However, the second part is that on the coarsest grid, we have to get an accurate representation of the operator. And for geometric multigrid, you have a really good idea what that is, because you can just form the original problem on the coarse grid and get a really good approximation of what it is and solve it. The algebraic multigrid, it's forming a coarse representation of the matrix, and it can miss things, especially things that couple the whole domain together. And because of that, we need to tell it things about the whole problem. So for instance, on a whole elastic problem, we know that the operator should be invariant under rotations and translations. Now, when we make coarse problems, we're not invariant under rotations, translations, normally because of boundary conditions. But we are nearly invariant because the boundary condition only operates in part of it. So when we're solving these coarse problems, they look mostly like problems without boundary conditions. And therefore, we need to tell the algebraic multigrid solver about these, what we call near null modes. Solutions that should almost not affect our problem. And that way, we can build them in to the coarse solution. Pilot does this automatically, so you could not worry about it. But I just want to tell you, because this can be a problem. And it was a problem for us initially before we automated this whole process. And that's the kind of operational knowledge that you need to use algebraic multigrid, even if you have no idea how it's making the coarse grids or coarse operators or how it's doing the solves. Even if you don't know that, you should know that this is what can go wrong. So that basically, if you do this, if you use algebraic multigrid and maybe a thinner linear solver like BiCG, you can get a really good elastic solver. So we could run tough elastic problems in Pilot and scale up very large, and we'd be fine. But what happens when you start adding faults? When you start adding faults, the formulation we have turns it into a constraint problem, solving for the forces of constraint necessary to get the slip that we want. And those kind of saddle point problems are very difficult in the sense that you cannot throw algebraic multigrid will not work on a saddle point problem. LU will not work on a saddle point problem. And so you have to do something special. And what we tend to do is we say, well, we really know how to do the elastic part by itself, and we pretty much know how to do the fault part by itself. And so what we'll do is we'll split the system apart and we'll solve the pieces that we understand, and then we'll put it back together iteratively. What this relies on is that you have physical insight for the pieces, which we do. We know a lot about elasticity. We know a lot about fault dynamics. And we have good solvers for each of the pieces. And then what you do is you can combine them together. And so we have a lot of different ways. This Jacobi combination is really just solve one, then solve the other. Solve them independently, update the whole system, and do it again. And this is what normally happens in these big climate codes like ESMF, that they solve the ocean, they solve the atmosphere, then they do it again. Gauss-Seidel is a slightly more advanced version of this, in which you solve one and update everything, and then you solve the next one and then update everything. It's less parallel because you cannot solve them at the same time. You have to wait for the last guy to finish before you can start the next solve. But it does converge faster. Now the last one, the Schur complement we've seen before, this is an exact way to put it back together. So it's more synchronous, it's more expensive, but these first two can outright fail, whereas Schur complements can always be made to succeed. So let's look at examples. So this is not just words. I like equations. I don't know how much you guys like equations, but I love them. They help me understand a lot of these things. So let me show you some sets of equations so you can get an idea about what these preconditioners are doing. Here is a prototypical system. I solve a lot of Stokes problems, but as you can see, the Stokes problem is also the Pilot problem in disguise here. A in the upper left, instead of being the Laplacian in Stokes, in Pilot it is the elastic, the linear elastic operator, or some nonlinear perturbations of that. B, instead of being the gradient operator as it is in the Stokes problem, is the set of rotations of the fault plane in the Pilot problem. And here is just the transpose. So suppose we have, this is a saddle point system. It's a saddle because you have a 0 right here. And suppose we start out with that. We'd like to form a preconditioner. Now, one of the simplest things you could think about doing, and this is what most of, say, these big code collaborative efforts do, is to solve one thing and solve the other thing independently. So we could have a preconditioner. We could have an approximate solve for the elastic part, A hat, and an approximate solve for the Lagrange multiplier, the tractions part. Now, what are these solves? So we give the field split to tell it to treat the field separately. We have additive, meaning solve them independently. For field 0, the elastic field, we say use algebraic multigrid. And for field 1, the fault tractions, we say, you know what, just use diagonal scaling. And since we don't have any further information, the diagonal scaling is just the identity. And so and at the bottom I'm giving the links to the papers that proposed these different variants. If we want to get a little more coupling, what we can do is we can say, well, let's solve one and then update and solve the other. So what happens here? We solve the elastic problem approximately with A hat. Then what we do is we update the fault tractions by acting on our solution with this B operator, in which in Pilot will map our displacements onto the fault, right? And so this gives us an update of our fault problem, and then we solve the problem for the fault tractions there. And this is, instead of being an additive method, this is called a multiplicative method. And so we just changed the PC field split type. Oh, there should not be an underscore between field and split there. I'm very sorry. I will fix that. To multiplicative. Now, if we want to, we can instead employ the Schur complement. What we can say is, well, let's use a Schur complement type of factorization where we approximately solve the elasticity, but instead of just having a system for fault tractions, what we have is a system for the fault tractions given everything we know about the elastic problem. In some sense, what you do is solve the elastic problem exactly and use that input to create just a problem on the fault. So you can do an elimination of all of the elastic problem to give a problem on the fault. Now, of course, that's very expensive, so what you tend to do is do it approximately. And so what we're doing here is we approximately solve the elastic problem, and then we approximately solve this reduced problem just on the fault. And one way to do it is to approximate the mapping of the elastic part onto just the fault. And this is what this Schur factorization type does. Here we just said use the diagonal, which is this very separated representation. And all of these variants are explored for the Stokes problem in mantle convection by Dave May and Louis Moresi in PEPI in 2008. If you want some stronger coupling between the elastic problem and the bulk and on the fault, you can add coupling, upper or lower coupling here. But the one that I think is most interesting, is this one. This is the full coupling. And this is what you would, if you multiply these three block matrices together, you'll see you get the original problem, A, B, B transpose 0, given the definition of S. And so we will use this full factorization as our gold standard. It's our replacement for LU for saddle point problems. So it's very, very useful for testing. I mean, basically what you want to do is always start with this to get an exact answer, to check your physics, check your boundary conditions, check your setup, and then start moving to some of these cheaper variants once you know that you have everything working. Just a quick note, we tend to use flexible GMRES on the outside. Why is that? In order to use GMRES, or many of the other solvers, the conjugate gradients, biconjugate gradient, you need to have exactly the same preconditioner at each step. But if your preconditioner involves subsolves on coarse grids or such, you can have a slightly different preconditioner because it iterates a slightly different number of times or such like that. And therefore, these flexible variants can take into account these differences among steps. And I just want you to be aware of this because this is something that can happen to you when you're optimizing, that you suddenly allow something to vary among the steps and your convergence is destroyed unless you're using flexible GMRES on the outside. It takes more memory, but it's more robust to these. So, yay, let's try real pilot examples. So this is my favorite part. So let's see if I can do the screen sharing now. So the first thing I want to do is do what I told you, which is try and use LU and have it, as I said, as the standard. But we'll try and use it on a fault problem. So, okay. So I think I can just do stop sharing and then share my screen. Oh,